Okay, welcome back. This is our first lesson on complex numbers, and today we're going to investigate things that only exist in our imagination. Let me start with this. Okay, this is very, very interesting. 5 times 5 is 25, and negative 5 times negative 5 is also 25. So if we ask what the square root of 25 is, we're asking what number multiplies by itself to give 25. We've already established that the negative case is ignored so that the square root only has one output, or so that the square root is a function. We say that the square root of 25 is just positive 5, not plus or minus 5. So we ignore the negative case. So we're asking what number multiplies by itself twice to give 25. We ignore the negative case, say that this is just positive 5. But if we ask the question up to this point, what's the square root of negative 25? We ask what number multiplies by itself to give negative 25. Up to this point, we've said there is no such number. We've said that this is non-real. There is no such number that multiplies by itself to give negative 25. But one day, and this is a good analogy, one day this math guy goes crazy. He decides, well, he's bored. He has nothing else to do. He says, I've learned everything I can learn, and I've got nothing to do. And so he's sitting here looking at this thing going, what if I decide to call this my imagination? He says, hey, let's call this the imagination, I for imagination. Well, let's be more specific. He didn't call this his imagination. He called this. Watch, let me show you. 1 times 1 is 1. Negative 1 times negative 1 is positive 1. So if I ask what the square root of 1 is, the square root of positive 1, we say what number multiplies by itself to give 1? Well, we ignore the negative case. We say that the square root of 1 is just positive 1. So he looks at the square root of negative 1. What number multiplies by itself to give negative 1? Well, if we multiply 1 times 1, we get a positive 1. Negative 1 times negative 1, we get a positive 1. What number multiplies by itself to give negative 1? There is no such number. So this, specifically, is what he decided to call his imagination. So this square root of negative 1 is the imagination. So he starts with, here, let me go ahead and get this down. All right, let's write the definition. We need to get this on paper first. Definition of the imaginary unit. What is the imaginary unit? This I is the imaginary unit. So he defines the imaginary unit to be the square root of negative 1 is equal to I. Now, if this doesn't blow your mind, I think the next part of the definition will. This is a two-part definition. I say this is not the primary part of the definition. The primary part of the definition is what I'm writing next. That the imagination squared is equal to negative 1. And this blows your mind. So let's look. This makes no sense. If I say 5 squared is positive 25. Because whenever we multiply a number by itself, we get a positive number. If I say negative 5 quantity squared, this is also positive 25 because this means negative 5 times negative 5, which is positive 25. So when we square a number, what type of result do we get? We always get a positive result. So this makes no sense to say that something squared is negative 1. Now, math people can't draw. Okay, math people can't draw. So this is the letter I. But because we can't draw, we get excited. Okay, so this is the letter I, but this is not a 2, this is not a 2, this is not a 2. This is the imaginary unit. Okay, so this represents I, the imaginary unit. It's not a 2. I write my 2's like this. Okay, this is a 2. This, don't get confused, is not a 2. This is a letter I representing what? Representing the imaginary unit. Now, the story goes like this. Okay, so this is a made-up story, but I think it gets the point across. But it's kind of, the concept is true. So this is based on a true story. Okay, so this guy decides one day, he says, hey, I'm going to call the square root of negative 1 my imagination. He starts playing with this, and he starts seeing what happens. Watch what happens. Okay, this is very, very, very interesting. It always excites me when I look at this, because it just blows my mind what happens with this. Watch. So he says, all right, let's make a chart. Okay, so we're going to make a chart, and we're going to say that I, the imaginary unit, must be equal to itself. That makes sense. 2 is equal to itself. 2 is equal to 2. So he says, well, the imaginary unit must be equal to itself. And we've defined that I squared is equal to negative 1. Well, here, let me trick you for a moment. Where does this come from? Well, this is not even really true. Watch this. So we say that the square root of 2 times the square root of 2, the square root of 2 times the square root of 2 is 2. The square root of 3 times the square root of 3 is 3. The square root of 5 times the square root of 5 is 5. So if we say I multiplied by I, or if we say I squared, we get I multiplied by I, or the square root of negative 1 times the square root of negative 1. So square root of 2 times the square root of 2 is 2. Square root of 3 times the square root of 3 is 3. Square root of 5 times the square root of 5 is 5. The roots cancel out. Square root of negative 1 times the square root of negative 1 is negative 1. So we say that I squared equals negative 1, and you just got tricked. This is not even true. Okay, so, let me be clear. This is our definition. This cannot be proven. You just got tricked. Okay, so how did you get tricked? I'll explain later. Okay, you just got tricked. So the I squared is defined to be negative 1. So we're going to assume that this is true. Now in the chart he says, and this is fascinating, he goes, well, if we have I must be equal to itself. And we know by definition that I squared is equal to negative 1. Now he says, what is I to the third? What means, okay, so I is I, and I squared is negative 1. What must I to the third be? Well, he says, well, I to the third would be I squared multiplied by I. We agree, we add the exponents. This is 2 and a 1. So I squared must be I to the third must be I squared times I, and I squared is negative 1 times I, which is negative I. So I squared is negative 1, I is itself, negative 1 times I is negative I. So he gets that I to the third power is negative I. Now watch this. So he says, I wonder what I to the fourth is. So I to the fourth, now we can do pick any 2, any 3, however you want to do this, it does not matter. I to the fourth is I squared multiplied by I squared. Remember, we add the exponents. I squared is what? I squared is negative 1. I squared is negative 1, so negative 1 times negative 1, which is 1. Interesting. So he says that I to the fourth is 1. Okay, so what's I to the fifth? Now he asks the question, what's I to the fifth? So I to the fifth, pick any 2, any 3, it does not matter. I to the fifth is equal to I to the second power times I to the third power. I squared is what? I squared is negative 1. Looking over here, I squared is negative 1. I to the third is negative I. And so we end up with negative 1 times negative I, which is positive I. So he says that I to the fifth is I. Watch, it does not matter. You can pick any 2, any 3. I to the fifth can also be written as I to the fourth times I to the first. I to the fourth is 1. And I to the first is just I. We get 1 times I, which is I. So it does not matter. Any 2, any 3, any multiple of these will give the same thing. So I to the fifth is I. Watch this. I to the sixth. What is I to the sixth? So he says, hey, I to the sixth must be I to the fourth. Pick any 2, does not matter. I to the fourth times I squared. Well, I to the fourth is 1. I squared is negative 1. So 1 times negative 1 is negative 1. So we get I to the sixth is negative 1. I to the seventh, can you guys guess? Notice. Negative 1, negative 1. What do you guess I to the seventh might be? Yes, I to the seventh is negative I. Watch this. I to the seventh, pick any 2. Does not matter. How about 3 of them? I to the seventh. How about we do I to the third, and I. So I to the seventh is I to the third times I to the third times I, which is I to the third times I to the third is negative I times negative I times another I. This gives negative 1 times negative 1 is positive 1. We get positive I to the third, and positive I to the third is defined to be negative I. So we see that I to the seventh is negative I. So I to the seventh is negative I, and now I to the eighth. What is I to the eighth? Just very quickly, I to the eighth is I to the fourth, multiplied by I to the fourth is one example. I to the fourth is 1, so we get 1 times 1, which is 1. So notice what's happening here. Notice there's a pattern. He discovers. I to the first is I. We have what? I, negative 1, negative I, 1. I to the fifth is I to the sixth is negative 1. Notice they match. I to the seventh is negative I. They match. And I to the fourth and I to the eighth match. So the question is, if I to the fourth is 1, I to the eighth is 1, what's I to the 12th? I to the 12th is also 1. What's I to the 16th? We're going up by multiples of 4. So I to the 4th is 1, I to the 8th is 1. What's I to the 12th? I to the 12th is also 1. So we end up with I to the 12th, just writing. We figure out that I to the 12th is a multiple of 4. So we say that I to the 12th is 1. What's I to the 16th? This is also a multiple of 4. This is 1. I to the 20th is 1. I to the 24th is 1. Every multiple of 4 is 1. Now what's fascinating about this is this guy starts playing with this stuff and he starts investigating, hey, there's patterns here. This is really interesting. It's our imagination. It doesn't even make sense, but we see that there's a pattern, a very interesting pattern. It's very fascinating to watch. So one day, this guy, this mathematician, he meets this physicist across the world. There's this physicist across the world who's been working for years on this problem, and he can't solve it. And so this math guy and this physicist meet up one day, and the physicist says, man, there's this math problem I can't solve. If I could solve it, I could complete this electric circuit. I could fully complete this electric circuit, but I can't solve this problem. The math guy looks at it and he goes, wait a minute, I can solve that. And the physicist says, how can you solve this? He says, because I've been playing with this stuff that's called my imagination. Hadn't even called it complex number yet. He said, my imagination, and I can solve that problem. And this definition, or the definition of the imaginary unit, which leads us into the study of what we now call complex numbers, is the reason problems that could never be solved before could now be solved. This was late 1800s, I believe. I'm not good on my history of math, but I believe it was late 1800s. Okay, so now problems that could never be solved can now be solved, and this led to the ability to make advancements in electronics, in radio, in many, many, many things. And this is the reason, because of this is the reason you have a cell phone today in your hand. Your cell phone, the technology to create that cell phone must, or I should say only exists because we have studied these things that only exist in our mind. It's very, very, very interesting. In radio, in order for radio to work, there is an imaginary component to radio waves. And this imaginary component, if it's not taken into consideration, we cannot create the technology to have radio, to have electronics, things like cell phones. So this right here is the whole reason for advancements in technology. This led to the ability, or what we call, I should say, this leads to what we call the fundamental theorem of algebra. That everything, algebra, all of a sudden broke loose. Every polynomial of nth degree has exactly n roots, meaning that a polynomial of second degree has 2 roots. A polynomial of third degree has 3 roots. Let me just give you a picture. Now, I've shown you this earlier this year. Okay, so this is how many roots? So we talk about x-intercepts. How many x-intercepts does this function have? We see 2. Okay, how many x-intercepts does this function have? Well, we see that there are 3 x-intercepts. We call these 3 roots. We call these 2 roots. Okay, now the question is, how many x-intercepts does this function have? Notice, it never crosses the x-axis, but it has 2. We can't see them. They exist only in our mind. Now, you're going to see seeing this coming later this semester. How many x-intercepts do your eyes see? You see 3. If I draw the same shape, how many x-intercepts does this function have? You only see 1, but how many are there? There are 3. And the other x-intercepts that you cannot see are called complex roots, or complex x-intercepts. Very interesting. We're going to study this later. Now, back to complex. So he discovers this pattern. We have to learn what a complex number is first. Okay, so he discovers this pattern. He says, well, I to the 12th is 1, I to the 16th is 1, I to the 20th is 1, I to the 24th. Every multiple of 4 is 1. So my question is, we're on page 280 of the textbook. So on page 280, we're looking at I to the 40th power. I to the 40th power. So the question is, what is I to the 40th? Can you figure it out? There's an interesting pattern here. I to the 40th. Well, we notice 4 is, I to the 4th is 1, I to the 8th is 1, I to the 12th, I to the 16th, I to the 20th, I to the 24th. So the question first is I to the 40th? Is 40 a multiple of 4? Yes, it is. So I to the 40th is equal to 1. Now my question is, what is I to the 39th? What is I to the 39th? Work backwards. If you have this chart written, work backwards in your chart one. I to the 39th is negative I. Now work backwards. I to the 38th. What does that mean? I to the 38th must be, go back one more, I to the 38th must be negative 1. And what is I to the 37th? I to the 37th, work back one more, this is I. And I to the 36th, notice that 36 is another multiple of 4. So 36, I to the 36 is equal to 1 again. So you see this pattern. Now let's look at some interesting cases in this pattern. Notice, if the exponent is even, either 4 or 2, or the exponent is 6 or 8, if the exponent is even, notice, it's either 1 or negative 1. So we say if the exponent is even, our answer is either equal to 1 or negative 1. Now, at least if you don't understand this, hopefully you will pick up on this, but if you don't understand this, you can at least make a 50-50 guess. Watch. So notice, if our exponent is odd, if we have 1 or 3, 5 or 7, the answer is either I or negative I. So the rule is this. If the exponent is even, our answer is either 1 or negative 1. In this case, it was 1. Notice our exponent is even. Our answer is what? Answer is negative 1. Exponent is even. Our answer is positive 1. If the exponent is odd, 39 or 37, the answer is either I or negative I. Here we have I, here we have negative I. Let's look at another question. Can you figure this one out? So first I want to see if you can figure it out. I to the 63rd. So we're looking at I to the 63rd power. Okay, so first off, give me a 50-50 guess. I to the 63rd. 50-50 guess here. 63 is even or odd? Hopefully you say, well, this is odd. Now I want you to find an even number. There's two even numbers that are next to 63. Hopefully you say there are two numbers even that are next to 63. It's 62 and 64. The question is, which of these is a multiple of 4? Is 62 a multiple of 4, or is 64 a multiple of 4? Hopefully you say 64 is a multiple of 4. So if it is a multiple of 4, I to the 64th is equal to 1. Now, this means if we work backwards in our chart 1, I to the 63rd is negative I. And if we work backwards one more, I to the 62 is negative 1. And lastly, I to the 61st is, going back one more, this is I. And I to the 60th, notice we get back to a multiple of 4, is 1 again. So if we use our chart, we can figure this out. But there's another trick. Okay, so if you're having a hard time figuring this out, there's another way you can do this. So we're going to look at I to the 63rd, I to the 63rd power. Another way to do this is to take 63 and divide by 4. Why are we dividing by 4? Because the pattern repeats every 4. So we're going to take 63 divided by 4. 63 divided by 4 is 1. We put 4 goes into 6 one time, so we put a 4, subtract, we get a 2, bring down the 3. 4 goes into 23 5 times. 4 times 5 is 20. Subtract, we get a 3. Now, so 4 goes into 63 15 times. We're not interested in this. We're interested in this 3. This is called the remainder. So we're going to say that the remainder is 3, and we're going to take the 63rd, or the 63 exponent out, and we're going to replace it with the remainder 3. So if we take the 63 out of there and replace it with the remainder, if we take 63, divide by 4, get a remainder, we can take 63 out, replace it with the remainder. So this becomes I to the 3rd, and I to the 3rd, we look in our chart, I to the 3rd is negative I. Now, going to I to the 40th for a minute, we're going to look at I to the 40th. Okay, so again, page 280, I'll write it here, page 280. Follow along on page 280. The problems that we're going to be doing are on that page. Now, I to the 40th. Okay, so 40. What are we going to do with 40? We're going to take 40 and divide by what? Take 40 and divide by 4. And if we go 4 into 40, we get a 10. 10 times 40 is 40. Subtract, we get a remainder of 0. Now, let's see. This is extremely interesting. Now, I've told you that anything to the 0 power, 7 to the 0 is 1, 8 to the 0 is 1, negative 153.2 quantity to the 0 power is 1. Anything to the 0 power is 1 except 0 to the 0th. We say that 0 to the 0th is indeterminate. This makes no sense. And don't worry, we're not going to call this our imagination, but 0 to the 0th is indeterminate. Makes no sense. So any number to the 0 power is 1 except for 0. But this only works where? Something to the 0 power is 1 only works in the real number system. This was only studied with respect to real numbers, numbers that make sense to us. Now we're studying numbers that don't even make sense. This is complex numbers. But what's fascinating is, watch this. What happens in the complex number system? So watch this. 1, negative I, negative 1, I. 1, negative I, negative 1, I. What's next? We have a 1. 4, 3, 2, 1, I to the 0. What is I to the 0 equal to? Whenever I see this, it just blows my mind. How could this happen? How could this happen? Things that don't even make sense. How can this happen? I to the 0 is equal to 1. Notice the pattern falls. 1, negative I, negative 1, I. 1, negative I, negative 1, I. 1. When I saw this for the first time, it blew my mind. This stuff doesn't even make sense. We have 4 possibilities, a probability of 1 out of 4. So a 25% chance that that is a 1. Yet notice that it falls perfectly in the pattern. 1, negative I, negative 1, I. 1, negative I, negative 1, I. 1. Blows my mind every time I see it. What do we have? 4, 3, 2, 1, 0. So we're saying here, even in the chart, that the imaginary unit to the 0 power is 1. Does that fall in line with what we've discovered with the real numbers? Yes, that a real number taken to the 0 power is 1. Look at this. The imaginary unit makes no sense. 0 makes more sense than the imaginary unit. But this is equal to 1. Now, so what do we say here? We take our remainder. We take our 40 out, and we replace it with the remainder. So we take 40 and divide by 4. We take the exponent 40, divide by 4, we get 10. 4 times 10 is 40. Subtract, we get what? A remainder of 0. So we're going to take the 40 out, replace it with the remainder. So 40 becomes, notice the remainder is 0. We're going to take the 40 out, replace it with the remainder. The exponent now changes from 40 to the remainder of 0, and I to the 0 is 1. And this is the same as I to the 40th. Very fascinating. So you can use this trick. If we look at number 25 in the textbook. Number 25 in the textbook says, so we're going to do the odd problems in the textbook. Number 25 in the textbook says I to the 25th power. So number 25 is I to the 25th power. And the trick is, well, there's 2 ways to do this. Either you can figure it out. What's the next multiple? What are 2 even numbers next to 25? Well, hopefully you say I to the 26th and I to the 24th. This is the fastest way to figure it out. I to the 24th. 2 even numbers next to 25. Which of those is a multiple of 4? Hopefully you say 24 is a multiple of 4, so this is 1. Now use your chart. If I to the 24th is 1, go 1 more. 1 more would be the same as I to the 5th, which is I to the 25th is I. Go 1 more. So I to the 6th is negative 1. I to the 26th is negative 1. Notice, if the exponent is even, the answer is either 1 or negative 1. So this is one way to do it. The other way to do this, we know that the answer is I. We know that the answer is I. If I write I to the 25th, okay, the other way to do this is to say, well, take 25 and divide by what? Take 25 and divide by 4 and get a remainder. How many times does 4 go into 25? Hopefully you say 6 times. Now we're going to take 6 times 4, get 24. Subtract, we get a remainder of 1. So we're going to take the 25 out of there and replace it with the remainder. So I to the 25th becomes I to the 1st, and we see that I to the 1st power is just I. So our answer is I. So there you go. This is how you do powers of I. And now, we're going to start with the lesson. So today, what are we doing? I guess this was just kind of getting you set up. Concepts of complex numbers, or what is a complex number, the imaginary unit. Okay, so we've talked really about imaginary unit. Now, what is a complex number? Complex numbers have 2 parts. So if I ask you, how old are you? Here, let me say this. Complex numbers have 2 parts, a plus bi. Okay, a is called the real part, and bi is called the imaginary part. Now, if I ask you, how old are you? If I ask you, how old are you? And you say, well, I'm 15 years old. Okay, no. Today you are not 15 years old. Today you are 15, well, I'll just say it. Today you are 15 plus 0i years old. Okay, so you're not 15 today. How many parts does your age have? Your age has 2 parts. You're going to see this in a minute. So we're going to investigate the real part and the imaginary part. So every complex number, this is one number, has 2 parts. Now I want you guys to put this diagram in your book. Okay, so if this set, inside, the small set is the real numbers. Okay, the real numbers. Real numbers is a huge set. Blows our mind. How many numbers are real numbers? Is the square root of 3 a real number? Yes. Is 5.2 a real number? Yes. Is 7/3 a real number? Yes. How many is pi a real number? 3.141. Da da da. Okay, this goes on forever. Is pi a real number? Yes. Okay, so how many real numbers are there? Infinitely many. Blows our mind. But the complex number system is a much bigger set. Complex number system is a much bigger set of numbers. It includes all of the real numbers and many, many, many more numbers. So we can say that every real number is a complex number. Your age, 15, is 15 a real number? Yes, it is. Okay, but is your age also a complex number? Yes, and complex numbers have two parts. So today, what are we doing with complex numbers? We are simplifying. Okay, now simplify means what? Add, subtract, multiply, and divide. We're going to start with addition and subtraction. Okay, so we're looking at question number 11. Question number 11 on page 280. Question number 11. These are really easy. These are actually very, very simple problems. Number 11 says -1 plus 5i. Add to this -2 minus 3i. Okay, so what operation here? Well, first you have to see this is a complex number and this is a complex number. Each complex number has two parts. Now I want you to tell me what is the real part of this complex number. The real part of this complex number is -1. The imaginary part is 5i. What is the real part of this complex number? The real part is -2. And the the imaginary part is -3i. So complex number has two parts, a real part and imaginary part. So what we're going to do is we're going to add the real parts together and we're going to add the imaginary parts together. Same thing as what we've always said. When we add, something must match, and what matches doesn't change. So this is very simple. We're add what matches. So add -1 plus -2, -1 plus -2, the signs are the same. We add, this is -3. And 5i plus -3i, here the signs are different, so we actually subtract. 5 minus 3 gives 2. Take the sign of the larger, which is positive, so you get positive 2i. Okay, so question, does the sum of two complex numbers result in a complex number? Yes, it results in a complex number with two parts, both a real part and what? An imaginary part. Let's see, imaginary, and when I'm talking I can't spell. Imaginary. Okay, so tell me, what is the real part of the answer? The real part of the answer is -3, and the imaginary part is 2i, and this is one number. This is one complex number. So today, what is your age? Out there, if you are 15, today your age is 15 plus what? Not just 15, 15 plus 0i. Your age has a real part, and your age has an imaginary component. This is extremely important for your SOL. Now, so there's a real part and there is an imaginary component to your age. So you're 15 plus 0i, but we will write the final answer as just 15. But you understand that your age has how many parts? Your age has two parts. The real part is 15. The imaginary part is 0i. So when you say I'm 15, what you mean is 15 plus 0i. So when your little brother or little sister comes up to you and you ask them, you say they're 3, 4 years old, you know, and you say, how old are you? And they say, I'm this many, and you say, no, you are 3 plus 0i years. No, don't do that. That would be me. I did that one time. I was just joking, you know, but to a little, and they looked at me like, what? I said, yeah, you're not 3. You are 3 plus 0i years old. So they looked at me like I was crazy. But anyway, okay. So adding complex numbers, we add the real part, we add the imaginary. Let's look. So we add things that match. Let's look at the next example. These are easy. So right now we are what? We are adding and subtracting complex numbers, something that we've already pretty much done in this class with other things. So we're looking at number 27. We have -3 plus I plus -4 minus I. We're going to add the real parts, add the imaginary parts. So we're looking here, real part is -3, imaginary part is I, real part is -4, imaginary part is -I, add the reals. So -3 plus -4 is -7, I plus -I is 1 plus -1 is 0, so we get 0I. write on your paper. I want you to write negative 7 plus 0i. How many parts does the complex number have? It has 2 parts. So we write this final answer. You can write your final answer as negative 7. But how many parts does the final answer have? The final answer has 2 parts. Negative 7 is negative 7 plus 0i, but when we write the final answer, we just write negative 7. But in your mind, you understand that this number has actually 2 parts. The imaginary component of this number is 0. Now, looking at number 29, I'll just put it here. Number 29, one more. This is 11 minus 8i. Subtract 2 minus 8i. And reminding you, when we subtract, we don't like to subtract, we like to add. So we're going to take the negative and do what? Take the negative and distribute, change the sign. So we're going to make this a negative 2, make this a positive 8, and we're going to add instead. So just make sure if you're subtracting, change your signs in the second number and change this to addition. Now, 11 plus negative 2 is 9, and negative 8i plus 8i is plus 0i. Go ahead and write this on your homework, and then write your final answer as 9, and in your mind you understand that this number has 2 parts. It is 9 plus 0i. But we write our final answer as just 9. Now, so we're done with addition and subtraction. Now we're going to move to multiplication and division. How do we multiply and divide complex numbers? Well, actually, I may split this, depending on how long the video is going. I may split this into multiplication today and do division in the next video. I'm not sure yet. Let's see how fast we can get here done with this. So looking at number 13 in your book. Number 13 says 6 minus 8i multiplied by 9 plus 2i. So we're looking at, here we have what operation between our complex numbers. You see a complex number and a complex number. Remember, when we added complex numbers, the result was a complex number. Here we are multiplying. So the question is, if we multiply complex numbers, is our answer going to be a complex number? And the answer is yes. Watch what happens. So notice binomial, binomial. We use the trick called FOIL. When multiplication meets addition, distributive property applies. The trick that we use is FOIL. Let's take the 6 and multiply by both. 6 times 9 is 54. 6 times 2i is 12i. Now take the second number and multiply by both. Negative 8i times 9 is negative 72i. And negative 8i times positive 2i is negative, be careful, negative times positive is negative 16. I times I gives I squared. Now, this is very interesting. Okay, so we look at this I squared. Never, ever, ever leave I squared, I cubed, I to the 4th, I to the 5th, I to the 6th on your paper. No, 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 no. I squared is negative 1. I to the 3rd is negative I. So you always convert. The only thing you should have on your paper in any final answer is either I to the 1st power or negative I. So all you should have on your paper is either I or negative I. You can only have an exponent of 1. So if you see I squared, exponent of 2, or you see I cubed, an exponent of 3, you always have to convert this. So never leave in your final answer an exponent of more than 1. So either positive I or negative I is the only thing you can have in your answer. So we look, what is our definition? It's right here. What is the definition of the imaginary unit? I squared is equal to what? I squared is equal to negative 1. So what are we actually looking at here? We're looking at negative 16 multiplied by negative 1. And if we do negative 16 multiplied by negative 1, what is this actually equal to? This is actually equal to positive 16. So I tell students, hey, I squared is going to change the sign of your number. So if negative 16I squared, this is negative 16 times negative 1. This changes the negative 16 to positive 16. So this is not written as negative 16I squared, but it's written as positive 16. Now, we add the real parts. 54 plus 16 gives 70. And now we add the imaginary parts. 12i minus 72i, the signs are different, so we're actually subtracting. 72 minus 12 is 60. So we get, taking the sign larger, negative 60i. And question, did the product of two complex numbers result in a complex number? Yes. Notice that the real part is 70 and the imaginary part is negative 60i. So the product of two complex numbers results in a complex number. And finally, let's look at, yes, I'm going to split this into two lessons because I need to discuss something else in the next lesson. Let's look at 3 plus 5i multiplied by 5 minus 3i. So here we have what operation between our complex numbers? What operation? Well, we have multiplication. So we're going to take the first number and multiply by both. This is a FOIL. 3 times 5 gives 15. 3 times negative 3i is negative 9i. And now take the second number and multiply by both. 5i times 5 is positive 25i. And 5i times negative 3i is negative 15i squared. Now, remember, I squared is never left on your paper. What is I squared equal to? Anytime you see I squared is equal to negative 1. So we're looking at negative 15 times negative 1, which changes the negative 15 to positive 15. So we have here 15 plus 15 gives 30. And negative 9i plus 25i, we add what matches. We add the imaginary components together. The signs are different. You subtract. 25 minus 9 is 16. So we get a positive 16i. So our final answer is 30 plus 16i. And the question is, did the product of two complex numbers result in a complex number? Yes, there is a real part of 30 and an imaginary component or imaginary part of 16i. That concludes this video. Good luck on your homework, and I will finish complex numbers in the next video.